Good afternoon, everyone. I am Dr. JONE PUKENAITE, and today I want to share the results with you from our pilot study using a transcutaneous cervical vagus nerve stimulation to support stress relief and better sleep. The study was funded by Pulsetto, but data collection and analysis were done independently by INVITA, where I worked as a study collaborator. We focused on two things that almost everyone struggles with: stress and poor sleep. And we asked a simple question: Can short home-based cervical stimulation sessions create measurable changes in stress and sleep quality? And my goal today is to share that signal with you. Further on here, next slide, please. This is where you can see the agenda, so you probably can read faster than I can explain it, but we'll just start with a problem, then we follow to understand the tool, the rationale behind the study, the pilot results, and we will finish with the invitation for collaboration for those that might be interested. Next slide, please. So, as you might know, stress and insufficient sleep are both common and clinically meaningful. Globally, about 4 in 10 adults felt stressed yesterday. Similar numbers report feeling worried, sad, and angry. And in the US, about a third of adults sleep less than 7 hours on workdays, and insufficient sleep is officially recognized as a public health problem. This is the clinical context for the cervical transcutaneous vagus nerve stimulation, and it highlights two large measurable burdens that our society aims to address. So given that burden, we go to the next slide. And here is what our device does and how we dosed it in our study. So Pulsetto is a non-invasive cervical vagus nerve stimulator used bilaterally at the neck around C6, C7 level. And each session lasted, and we used it at the intensity level of 5, or in electrical impulses language, it's 4.7 VPP. All sessions were logged through the app for adherence, and no serious adverse events were observed, only mild, short-lasting skin sensations. So let me now show you what this stimulation does physiologically. In the next slide, you will. So this slide shows the modeled electric field at our study dose of 24.7 VPP. The map shows how the field concentrates around the carotid S-half, where the cervical vagus nerve lies close to the surface. Warmer colors mark stronger stimulation in this vagal region, while cooler areas show nearby muscles and deeper tissues that stay unaffected. On the right, the blue line shows how field strength increases with voltage. Pulsetto can cover the full range, but we stopped at 24.7 VPP, and A delta sensory fibers of vagus nerve are recruited. These fibers send afferent signals to the nucleus tractus solitarius in the brainstem, which helps regulate autonomic tone, stress, and sleep. So next, let's see how the activation translates into physiological and clinical outcomes. So at 24.7 volts, TCVNX likely activates A beta and A delta sensory fibers that project to the brainstem, increasing parasympathetic tone and stabilizing the HPA axis. So this pathway is well described in the literature. So based on the mechanism, we expect rapid calming and gradual sleep improvement effect. That's exactly what we observed in the study. So if we go to the next slide, here the slide summarizes our study design and endpoints. We enrolled 40 adults, randomized them to unilateral and bilateral cervical stimulation. Our primary endpoints were validated clinical scales for depressive symptoms, anxiety, and sleep. We also measured hair cortisol and cortisone as exploratory biomarkers to assess longer-term HPA axis regulation. So this slide essentially sets up what comes next. First, we will go through clinical outcomes, and then we will see the biological marker results. So next slide. We are, no, I'm sorry, go back one slide. Yeah, here. Here are the 4-week outcomes from our randomized pilot. Across all validated scales, we saw a clear and consistent pattern. So depressive symptoms, PHQ-9, dropped by 56%. Anxiety, we measured it by GAD-7 scale, dropped by 45%. And sleep disturbances, PSQI, by 41%. So most of the improvement occurred within the first 2 weeks, and then it stabilized and strengthened with the continued use. The graph shows this steady decline across time, highly significant at all measures. So p-value below 0.001. Both unilateral and bilateral groups improved similarly, so results are shown as pooled means. In the next slide, we can see we analyzed paired hair samples from 37 participants before and after. 70% showed lower cortisol, which with mean levels dropping from 6.7 to 4.9 milligrams, and a p-value was equal to 0.013, and driven mainly by bilateral stimulation. Cortisone showed a similar downward trend. P-value was at 0.059, and both markers were correlated. So rho was equal 0.50, and p-value was 0.002, suggesting HPA axis modulation, like a shared HPA axis modulation. So in short, these biomarkers shifts these biomarker shifts mirror the questionnaire results, showing both physiological and biological evidence of stress reduction. In the next slide, I summarized everything. So within 4 weeks, TCVNS led to significant improvements in stress, anxiety, and sleep scores, along with parallel drops in hair cortisol and cortisone. The strongest effects were seen with bilateral stimulation, and safety was excellent. No serious observable changes in both perception and biology. Safely and within weeks. So in the next slide, now that we understand the mechanism, this is where it all comes together. Our data in prior research shows that TCVNS activates vagal sensory pathways reaching to the NTS and the brainstem hub that regulates autonomic HPA axis balance. From there, signals extend to regions that influence stress, sleep, inflammation, metabolism. That's why TCVNS has potential far beyond stress relief. It's a systems-level tool that can modulate brain-body communication across multiple domains. So the question now is not if it works, but how precisely we can measure and validate these effects across different conditions. So in the next slide, it brings us to the next step and how we can collaborate to build the mechanistic and clinical evidence that defines this field. At the core, our next step is a larger randomized trial on sleep and stress, building on these pilot signals. Alongside, we are opening collaborations in inflammation, pain, PTSD, and the gut-brain and metabolic domains. All these areas link through the same vagal brain circuitry. So the opportunity now is to validate and expand these effects together. So going to the next slide, in summary, TCVNS can shift both the perception and biology of stress, as we have seen. The vagus nerve isn't just about relaxation, it's a regulator of sympathetic balance between brain, body, and metabolism. So I really thank you for your attention. And if this research area resonates with you, you can find me on LinkedIn or use the QR code and book a call with me. I would love to explore further research ideas together. And of course, if you have any questions, I would be happy now to also have a discussion if we have some time left.